So let's have a look now at proposition 40. That's proposition 40 according to Heath's numbering. So it says that if q and q primed are any points on opposite branches, obviously of a hyperbola, and lowercase v is the midpoint of q primed, then CV, the line joining that midpoint to the centre, is the secondary diameter to the transverse diameter drawn parallel to q primed. I just want to comment on this here. This is more or less Thomas Heath's wording in his translation, and he uses this word here, secondary diameter, and he does include it in the inverted commas just like I've done here, and it doesn't explain why it's in inverted commas, but presumably it's because he's not using the words or the phrase secondary diameter in its strict sense here. So in an earlier video, I think video 3, third part, I said that a secondary diameter is, so given a hyperbola or an ellipse, and you've got a transverse diameter and you've got the parameter of that diameter, the secondary diameter is a mean proportional between the length of that transverse diameter and the parameter. Well, there's no guarantee that actually CV, the length CV, is going to be a mean proportional between the length of PP primed here and its parameter. So, however, CV is going to be a conjugate diameter. So I would have personally used the word conjugate in here rather than secondary diameter, but that's just my a comment that I wanted to make on that. So let me just explain now the diagram that we've got here. So we've got a hyperbola, and we've chosen our points q and q primed, and lowercase v is the midpoint, c is the centre of the hyperbola, and what we've done is we've drawn a line, we've drawn the chord q primed, and a line that passes through q primed and the centre that is continued until it meets the hyperbola again at this point here, this lowercase q. So then the chord q, uppercase q and lowercase q is formed, and we draw a line through the centre parallel to q primed. That's pp primed here, which will be a diameter of the hyperbola, and produce pp primed to meet q at v. What we want to show is that pp primed actually bisects this chord at the point v. So just because this is a diameter doesn't mean that it bisects this chord here. It will bisect it only if it's a particular type of chord, the right type of chord. So we want to show that this is actually the right type of chord. A proposition that I'm going to use in this is proposition 10, which I've not mentioned in any of my videos, but what it says is that any chord of a hyperbola or an ellipse that passes through the centre is bisected at the centre. So therefore this line q primed q, because it's a chord that passes through the centre, it must be bisected at the centre. So we're going to make use of that proposition even though I've not actually proved it. Okay, so let's make a note of that. That q primed, CQ primed is equal to QC. Okay, and we've also got that because this lowercase v here is the midpoint of QQ primed, that QV is equal to VQ primed. And now let's just have a look at this triangle that we've got in here. So this Q primed, lowercase q. So Q primed V Q Q C. So both of these together, that CQ primed is equal to QC, that would mean that CQ primed is equal to a half QQ primed, and also VQ primed equal to QV means that VQ primed is equal to a half QQ primed. and therefore this line CV cuts the sides of this triangle proportionally, in the same proportions. So therefore, using Euclid, by Euclid Book 6, Proposition 2, we can say then that the line CV is parallel to QQ. Okay, so any line through a triangle that cuts two of the sides proportionally must be parallel to the third side. Okay, so that means then that this QVCV must in fact be a parallelogram. So it must be a parallelogram because QV is parallel to VC or CV. So that's by construction of the line here. And we've just shown that CV is parallel to, if it's parallel to QQ, then it must be parallel to QV as well. So we've got a parallelogram here. So in particular, we can say, therefore, that QV is equal to CV. And we can also say that QV is equal to VQ primed, and that's equal to CV. So let's just have a look now at these triangles in here, in particular triangle Q primed V and C, and C lowercase q V. Then because these are similar triangles, then the ratio of Q primed C to CQ must be equal to the ratio of V or CV to QV. But Q primed C is equal to CQ. That's what we've got from up here. So these are equal, and therefore these must be equal as well. So we get that QV is equal to CV. But CV we've already shown to be equal to QV. So paying particular attention to these two, that means that this chord Q, uppercase Q, lowercase q, is actually bisected by this diameter PP primed. It's bisected at this point V. So let's just sum up where we are. QQ is bisected by the diameter PP primed, and QQ has been shown to be parallel to CV. So therefore, thinking about what I did back in, I think the third video that I made at the start of the third video, part 3a, I showed that a transverse diameter will bisect all of the chords parallel to the conjugate diameter, and the conjugate diameter will bisect all of the chords parallel to the transverse diameter. Well, this is parallel to the conjugate diameter. So this is parallel to CV. So because CV passes through the center, then it must be a diameter. And it must be, because it's parallel to QQ, it must be the conjugate diameter to PP primed. So it's not, I personally wouldn't have used this, the secondary diameter. I'd think of it more as a conjugate diameter, although obviously if the right length is taken on there, then it will be a secondary diameter as well, depending on the ratio between pp primed and its parameter and things like that. But at least we've got a conjugate diameter. CV is actually a conjugate diameter. So here we get that QQ is bisected by PP primed, and we can conclude that CV is a conjugate diameter. So a conjugate diameter to PP primed, that is, and that completes the proof. So the next main result that I want to go through is proposition 46. So that's proposition 46 according to Heath's numbering of Apollonius's propositions. But before I do that, I just want to go through the results of proposition 45. So I don't want to go through this in a lot of detail. I'm going to go through it in quite an informal way, but we're going to need the result from this proposition when it comes to proposition 46. So proposition 45, what it's concerned with is finding some of, if not all of, the axes of a conic section. So there's three different cases: hyperbola, ellipse and parabola. So in the case of the hyperbola, if this is our hyperbola here, two branches, then using proposition 44, which I haven't mentioned, but proposition 44 gives a way of finding the centre of a central conic section, so a hyperbola or an ellipse. So using proposition 44, we'll locate the centre of the hyperbola, and we'll choose an arbitrary point on the hyperbola, so P for example. And then with centre C, we'll describe a circle, which is what you can see here, which passes through the point P. And this circle will intersect the hyperbola in at least 4 places. Now, strictly speaking, at this stage, we haven't proved that it's not going to be more. That's something that's covered more in book Apollonius's 4th book, to deal with intersections of different conic sections. But I think it's fairly clear to see that there is only going to be 4 intersections. We only need 4 anyway. So we've got P, Q, Q primed and P primed. So we draw the chord PP primed here and the chord PQ here. So notice that PP primed, this chord is on a single branch and the chord PQ is joining 2 points on separate branches. And we find the perpendicular bisectors of these 2 chords. So not only is PP primed a chord, and PQ actually, not only are these chords of the hyperbola, but they're also chords of this circle as well. So going back to really elementary geometry here, the perpendicular bisectors of chords of a circle will pass through the centre. So if we bisect PP primed at N and draw the perpendicular bisector of PP primed through N and the perpendicular bisector of PQ through M, the midpoint of PQ, then these two are guaranteed to pass through the centre of the circle, which was also the centre of the hyperbola. Not only that, so that's these 2 blue lines here. So these are definitely going to be diameters of the hyperbola, because any lines passing through the centre of the hyperbola must be diameters. So they are diameters, but because they intersect their chords, these were kind of arbitrary chords. So they bisect these chords, PP primed and PQ, but not only that, they bisect them at right angles, so therefore they must be axes of the hyperbola. So that's a way of finding 2 axes of a hyperbola. It turns out that there aren't any more axes. Actually, that's the proposition 46 that I'm wanting to go on to in a second, proving that there aren't actually any additional axes to the ones that we've just found. Similarly for the ellipse, it's basically the same argument. We find the centre of the ellipse using proposition 44, and choose any point P on the ellipse and draw a circle with centre C and passing through that point P. And again, the circle, it's going to intersect the ellipse in at least 4 places. Quite obvious that it's not going to be more, but strictly speaking we haven't proved that yet. And again, we form the chords PP primed, PQ, find the perpendicular bisectors, perpendicular bisectors of chords of a circle, pass through the centre of the circle, which in this case is also the centre of the ellipse. So these lines, these blue lines here, which are the perpendicular bisectors of PP prime and PQ, must be diameters, because any lines passing through the centre of an ellipse are diameters. But not only that, because they they bisect these chords at right angles, they must be axes. So again, this is a way of finding the axes, 2 of the axes at least, of an ellipse. Proposition 46 will address the issue as to whether there's any additional axes. And then for the parabola, it's a different argument altogether, but it's not a very difficult argument. So we've got our parabola here. All we do is we draw a diameter to the parabola, any diameter, and this can be this diameter can be found using, again, proposition 44. So there's actually 2 parts to proposition 44. So we drawing an arbitrary diameter, PD, and then we draw a chord, QQ primed, of the parabola perpendicular to that diameter. So just to emphasize that that is a right angle in there. So we've got QQ primed, and then we bisect QQ primed at the point N, and we draw a line parallel to PD through N. So since this PD is a diameter, it must be parallel to the axis. So this is proposition 20 that says that, which I proved in one of my earlier videos, I think video 3B. So because this line is parallel to this line, then it must also be parallel to the axis, and therefore it must also be a diameter. But because it bisects QQ primed at right angles, it must actually be the axis itself. And in the case of the parabola, it's quite obvious that there is only one axis, there is only one line that can be described as an axis. So proposition 45 just allows us to find some of the axes, potentially all of them, but we'll see in proposition 46 whether there are actually any additional axes. So that's just a quick summary of proposition 45. I'm going to move now on to proposition 46. So moving on now to proposition 46 in Heath's numbering of Apollonius's work. The proposition states that no central conic has more than 2 axes. So when we talk about a central conic, we're talking about a hyperbola or an ellipse. We're not talking about a parabola here, and we're not talking about circles. So it's definitely restricted to hyperbola or ellipse. The phrase central conic refers specifically to those types of section. So we need to consider the 2 cases separately, hyperbola and ellipse. So I'm going to concentrate on this just for a few minutes. So let me explain the diagram that we've got. So we've got the hyperbola here, and just like in the previous proposition that I was talking about, we find the centre of the hyperbola, choose a point P on the hyperbola, and with centre C, we draw a circle, we describe a circle that passes through the point P that we chose. So that's, I've not drawn the whole thing in here because it would be too big otherwise. But this is an arc of that circle that we described, so it intersects the hyperbola also at this other point P primed down here. And just as before, join those 2 points PP primed, find the perpendicular bisector, and so bisect PP primed at N, and CN is that perpendicular bisector, and that is, just as in proposition 45, an axis of this hyperbola. There's also going to be another axis CM up here, which I've not drawn on from the chord PQ, so just as in proposition 45. What we're going to assume in this case is that there is actually another axis somewhere. So that's this line here, CL. Okay, so it's an axis that is other than CN or CM, so it's some third axis in there somewhere. So what we're aiming for here is a contradiction. We're wanting to show that under the assumption that CL is an axis, we get some kind of contradiction. So let's have a look. Well, with CL being an axis, that means that it bisects chords, all of the chords that are perpendicular to it. So let's draw the chord through P primed that is perpendicular to CL, and which when produced will meet the hyperbola again at the point R up here. So P primed R is the chord bisected at the point CL. So the diagram is a little bit exaggerated here because we do actually have that P primed L is equal to LR, even though it doesn't look like it from the diagram. We're going here on the information, what we're told or what we know, what we've assumed about the properties of this line CL. Okay, so let's have a look now at the triangles formed by CRL and CLP primed. Okay, so these are both right angles. So angle CLR is equal to angle CLP primed. That's due to the fact that CL is supposed to be an axis, and therefore it bisects this straight line P primed R at 90 degrees. So these must each be 90 degrees. We've also got that P primed L, so this line here is equal to LR, so it's equal to that line. And obviously CL is common to both of these triangles, so obviously those two sides are equal in length. So that means actually that triangle CRL is congruent to triangle CP primed L. So therefore we get that so CR is equal to CP primed. But not only is CR equal to CP primed, we've also got that CP primed is equal to CP. Remember that P and P primed both lie on a circle centered at C, so CP primed will both be radii of the circle, and therefore they've got to be equal. So what this is saying is that this circle that passes through PP primed must also pass through the point R. And this is our contradiction, because Apollonius argues that clearly the circle cannot intersect one branch of the hyperbola at more than 2 points. Now, from a modern kind of perspective, that might not be acceptable to just simply say, well, it's obvious from the diagram. There might be a bit more rigour required in modern treatments of this, but this is Apollonius's work. Apollonius is king here, so we go along with what he says. Apollonius says that it's not possible for the circle passing through P and P primed to actually pass through a third point, which is suggested by this. Therefore, that is our contradiction. It's therefore CL is not an axis. So that's the contradiction right there. So that finishes the case for the hyperbola, so I'm going to move on now to the case for the ellipse. Let's have a look now at the case of the ellipse for this proposition 46. And this is the relevant diagram for this particular part of the proposition. So we've got the ellipse in here. I've not drawn it all in because we don't need the whole ellipse drawn in. And just as before, we find the centre of the ellipse using proposition 44, and we choose a point P on any point on the circumference of the ellipse, and we draw a circle with centre C passing through the point P, and that will intersect the ellipse here at the point P primed as well. Join the points P, P primed, and find the perpendicular bisector of that chord, which makes this diameter indeed the major axis of the ellipse, AC. And we've also got the minor axis, which we can find in a similar way, BB primed. So BB primed is the minor axis. So they're the two axes that can be found using proposition 45. What we're going to assume now is that there is actually a third axis in there somewhere. So this CL here is the third axis that we're going to assume exists. So we're going to draw a line perpendicular to CL, a chord, perpendicular to CL. So that's P primed R is the chord that we draw. So that's going to be bisected at the point L, and both angles CLR and CLP primed are going to be right angles. We're going to draw lines ordinate-wise from the minor axis to the points P and R. So the angles CHP and CKR are also going to be right angles, with this being an axis. And we're going to join P and R to the centre. Notice that the circle that we've drawn will necessarily have a radius that is less than the length of the of this line CA, which is half of the major axis of the ellipse, but it's going to have a radius that's greater than length CB or CB primed, which is half the length of the minor axis. This is going to be significant further down the line. So again, we're going for a contradiction here with this. We've assumed the existence of a third axis. We're hoping to arrive at some kind of contradiction to show that we're actually mistaken, that this is not actually an axis. So let's see how we get on with that. Some observations that we can make straight off the bat. Because RK and PH are both ordinates to the minor axis, then we can say that the ratio of RK squared to BK times KB primed is equal to the parameter, so it's the parameter with reference to the minor axis, so I'll just call it P sub B, the ratio of that parameter to BB primed. So this is what I went through in the second video that I made on the treatise. Similarly, we've got that PH squared ratio BH times HB primed is equal to the same ratio, and therefore RK squared to BK times KB primed is equal to PH squared ratio BH times HB primed. So this is going to be something that we're going to use later on. So I'll just make a note of that. Okay, and similarly, as in the case with the hyperbola, we can actually show that CR, the length of CR, is equal to CP and CP primed. So it's roughly the same kind of argument. So we've got the triangle CRL, and remember that's going to be 90 degrees, and we've also got the triangle P primed CL, again, that's going to be a right angle because the P primed R is bisected by CL. So LC or CL is a common side to both of these triangles. Because P primed R is bisected at L, then LR is equal to P primed L. So using congruence criteria, we can say that triangle CRL is congruent to triangle CP primed L. So therefore, the length CR is equal to CP primed, which in turn is equal to CP. In particular, we're interested in CR being equal to CP because that means that CR squared is equal to CP squared. But CR is the hypotenuse of the triangle, the right angle triangle, obviously, CRK. So therefore, CR squared is equal to RK squared plus CK squared, and CP squared is equal to PH squared plus CH squared. So they're equal to one another. And therefore we get that C, which one do I want? PH. RK squared minus PH squared is equal to CH squared minus CK squared. This is another equality that we're going to need to use very shortly. Okay, the next thing for us to look at is what we've got going on here with the minor axis. So I'm going to draw out a couple of diagrams to help us with this. So let me think. So we've got B, K, C and B prime. So what we can say, because of this particular setup, because B primed is bisected at C and K is just another point on that line, we can say that B primed K times KB plus CK squared is equal to CB squared. Now this seems like a bit of magic. Where did this come from? This is from Euclid, Book 2, Proposition 5. That says this. And in a similar way, we can say that B primed H times HB plus CH squared is also equal to CB squared. So both of these follow from the same proposition in Euclid. Okay, so we can put these together now. So let's move over here. So what do we get? Just kind of rearranging them maybe. In fact, no, I don't need to rearrange them. We can say that B primed K times KB plus CK squared is equal to B primed H times HB plus CH squared. So that's just equating these two quantities here, because they're both equal to CB squared. So therefore, I get that CH squared minus CK squared is equal to B primed H B prime K times KB minus B primed H times HB. And we're going to need this, because this and this together allow me to say that RK squared minus PH squared is equal to B primed K KB minus the rectangle on B primed H and HB. So I'm going to go through this quite carefully now, the next stage. I just want to highlight this because it's something that's important and we'll need to come back to this in a few minutes. So we need to go back up to this now, up to this equality up here. So we've got RK squared ratio BK times KB prime is equal to PH squared ratio BH times HB prime. So rearranging this, we get RK squared ratio PH squared is equal to BK times KB primed ratio BH times HB primed. I can't remember which, back in the first video, right at the end, I wrote down a load of rules of manipulations for ratio. I can't remember exactly which one it is, but it's one of those. And then we're going to use something like separando, for example. So what I'm going to get is RK squared minus PH squared ratio PH squared is equal to BK times KB primed minus BH times HB primed ratio BH times HB primed. So all I've done is subtracted the antecedent in each case from, the consequent in each case from the antecedent, and then replaced the old antecedent with that difference. So I know that this RK squared minus PH squared is equal to this, because that's what I've shown here. So therefore PH squared is equal to BH HB primed. But in a similar way, I can also show that RK squared is equal to BK times KB primed. Okay, so these are the things really that provide us with our contradiction, because these are effectively the intersecting chords theorem. Euclid's book 3, one of the propositions in book 3. And the intersecting chords theorem is valid in circles. It's not valid in ellipses. It's only valid in circles. So what this is saying is that our circle that passes through the point P must also pass through the point R. Not only that, the circle must have a diameter BB primed. But remember what I said earlier, the circle here passing through PP primed necessarily has a radius that is smaller than this AC, half the major axis of the ellipse, but it's also got a radius that is necessarily greater than CB, half of the length of the minor axis. So therefore the diameter of the circle has to be greater than the minor axis. So the diameter of this circle can't be BB primed. So this is our contradiction. So here we can conclude that CL is not an axis. So that is our contradiction. And that finishes the proof of this proposition. So that brings us to the end of this video, and possibly to the end of this series of videos. I set out really to give a kind of introduction, a series of videos that give a bit of an introduction to the works of Apollonius, some of the results, and some of the techniques that he uses. And I think I've really covered as much ground as I can relating to the specific techniques that Apollonius tends to use. So manipulation of ratio and proportions, and similarities, congruence, and application of areas. And I've gone through some of the constructions in some of my videos. Really, from this point forward, this brings us to the end of Apollonius' second book. The end of this video brings us to the end of Apollonius' second book. And the rest of the work really uses similar techniques. It's really just the level of ingenuity with which Apollonius applies them, but there's not really any new techniques that I can really introduce. There are some interesting results further down the line, but I'm going to leave it up to anybody that's interested now to discover those results for themselves. In future, I might make some more videos. I'm going to leave the possibility open. If I do, then it's possibly not going to be Heath's translation that I continue on with, unless I really feel that there's something that I want to go through in particular. But I might make some videos covering some material from maybe some other version, some other translation of Apollonius' work. Only time will tell. So I want to thank anybody that's managed to get through all of the videos of this series, or even if you've just managed to get through this particular video. And normally I say I'll see you in the next video, but on this occasion I won't, at least not in this series of videos. But thank you for watching all the same.